I'm going to talk about Tablegen, which is it's a pretty important tool in LLVM. It's used to describe a lot of the parts of the compiler. So I'm going to give basically what this talk is more or less is sort of what's missing in the documentation in Tablegen, so people that need to use it can understand it better. What people tend to do is just to copy ones from other ports, and that tends to mean that everyone just keeps copying the same mistakes everywhere. And people don't really understand how it works, and I think if they do, they could make a little better use of it and do a better job at that, and also to avoid some, I found several bugs that have been in all of the ports for ages just by once I started to understand how Tablegen worked better. So I'm going to be adding some information to that. What I hope to do too is to create some interest in documenting Tablegen better. Right now there's some kind of loose user's guides, but I'd like to see there be a grammar for how it works, so it'd be a little clearer language, and develop some more documentation. The original, I think, intent was to actually describe a lot more of the compiler in a sort of a Tablegen-like language, but right now Tablegen itself is kind of hard to understand, and it's, even just as a very simple data definition. So I think if we get a handle on it better and define it better, then it's possible to grow it into something more significant than just a data definition. So it has several uses. The main use is, though, is to describe the target machine to LLVM. And it has a lot of things about it that are oriented towards that application. One thing is that you tend to have, you're trying to match up a lot of times the definition of the Tablegen for the compiler with the documentation for the machine. And that stuff tends to get spread out throughout the manual. You see like an instructions defined somewhere, another instruction, and when you're forced to all put it in one place, it's kind of hard to match it up against your original documentation. So it's designed to kind of allow the sort of distributed flow and then have it be collected at the end. And it seems like it does a fairly good job of that. They've added things over time to try to do the different architectures. And there's a lot of duplication when you look at an architecture manual. There's a lot of duplication, like somewhere they define something that's duplicated everywhere, and you want to avoid doing that all the time because it creates bugs. Because you don't copy it correctly, or you find a mistake and you have to fix it in a lot of places. So there are 3 documents right now that talk about Tablegen, and I'm basically trying to fill in the holes. So hopefully after you hear this talk, you can go read these other documents and it'll all make perfect sense to you. And I think that's basically true. When we were doing the dry runs for my talk, a couple guys that hadn't actually worked on the compiler a lot but had a lot of compiler experience, once I gave my dry run, they were able to go through the other stuff and understand it pretty well. So I think hopefully I'll achieve my goal here. So the first thing to understand about Tablegen is actually, it's basically a text processor, the first part of it. It's like a template macro processor. And you can think of these classes, there's various classes that they call them, and then records, which is the actual data. And classes are basically just types that are used to simplify generating, creating a lot of, data that has common elements to it. So the first one basically is going to expand, just like the C preprocessor expands, parts of the C language and then into a simpler form. And then, but it's really just a textual thing. It's like XML. It doesn't really have any meaning. And so the second pass is there's a many application-specific backends. So it kind of parses this thing and expands the text, and then the backend kind of has an abstract syntax tree essentially to work on. You can collect the information and go through it. But each backend, whether it's a backend to generate parts for the compiler to do register processing or instruction selection and different things, they're all like separate applications really. And it's a little confusing because, so like I said, the way XML works is XML doesn't mean anything by itself. What means the XML is the application, whatever reads the XML afterwards. So this thing produces sort of this generic backend, and then each backend has to interpret it totally differently. And it's kind of confusing because they actually link them all together. So even though there are all these separate applications, when you run Tablegen, it's just Tablegen. And then based on what options you give it, it kind of calls a different backend, but the backends can be really different. Like one could be for option processing and have totally different meaning. But it's confusing because it makes you think it's one language, but it really isn't. It's one common macro preprocessor, and then n totally different backends and interpret the text however they decide to. Now, there's one important exception to this, and this is also confusing when you first start to understand that it is really kind of this front-end processor, and that is that there's a little more information. Like when you run like the C preprocessor, once it's done, it's all expanded. There is no more information about what originally was there. Maybe sometimes there's comments if you turn on some kind of comment option. But in this, it's not quite, that's basically true, but not exactly true. And so what's not exactly true is that when you have record definitions that were based on classes, they're all expanded, but you still know, in the end of the day, the data is just the records. That's really all the backend really cares about. However, it does know what classes they came from. So the backend processor can, for example, go through and find out every data record that came from that was derived from a class record that was of register type, for example. So you can create all these different data records for different parts about the information about the registers, and then in the end, though, when the tool runs, it can find all the information about registers and collect all those data records together. And that's something that you wouldn't find in a normal macro preprocessor. Once the stuff is expanded, that's lost. And this is just important for how you understand it. So then I talked about this. You can actually find out about which backends are there by running these help commands. And I don't want to do like a lot of questions, but if there's something that's really like nagging you as I'm talking, you're welcome to ask, because I hope this is tutorial-ish, so I want people to understand and not lose people on this. So there's a couple of places also besides my talk and the other documents I listed where you can learn a little bit more about this. One thing is there's actually a test directory inside the LLVM directory that's under test, under Tablegen. And some of these are really not that useful. They're just regression tests, but most of them are really unit tests for Tablegen. So you can actually run Tablegen on those, the front end of it, and look at what output it produces to see if you understand what's going on there. So there's all the various features. You can find an example of that, basically, a pretty complete example, and run Tablegen and look at the output and say, oh, I see. Or if you try to guess what the answer is and see if you can test yourself if you understood it. I've also created another Google code. I've done this before, and probably they don't like me doing this because they like to have everything be inside of LLVM, but I personally find that I can be more creative outside of like a million people questioning my check-ins inside of LLVM. So for this kind of thing, I've actually created another place to try to develop some more documentation and do some of these things so that I can control it myself and not have to argue with people about everything I want to do. So you can go there. So I've created this alt LLVM table, and it's really just to work on the documentation and do some further work, and then with the idea that it will be put back eventually if they'll let me do it, if they like this stuff. So actually this presentation is in there, and I have some other sample code. And in this talk, actually, there's a bunch of sample code that are examples also, and there's those are also separately inside there too, so you can actually take those examples and run them yourself and try them afterwards. And it should actually be on this site too for the talk, not only the slides itself, but also a tar file with examples. So also this area too would be a place to try to like work on the BNF and to have some more documentation and do this so that it's a little bit easier than trying to deal with the normal kind of check-in engine. So you can just run Tablegen by itself, and it will print out a lot of things. It will basically run the front-end processor. I kind of already mentioned these things. You can go find you can also go look for various main TD files. That's the extension they use, and you can also run the tool just on that itself without running the application-specific backend to understand how the various things are expanded. Because basically that's kind of the tricky part. Once you start to understand how the various things are expanded, then you have a lot more freedom. You can use the language more fully rather than just kind of cutting and pasting from other ports that have been done. So anyway, this is some places you can look for more examples. Okay, so I'm going to just kind of go through, and I basically picked some things that I think are illustrative of the things that would, most people, we all know how to program, so I think most of it, once you sort of see the example, you start to catch on, but I tried to provide what I thought were the kind of minimal examples. So So here's a very simple example where I have a record type, which is basically, the record is basically your data element that one of the backend processors is using. The classes are only really used essentially to help make that easier to enter, except for that one exception I gave earlier where where the backend will know what class the data came from if you use that. So here's an example of essentially you get the same data record, but in one case, there is no class associated with it. It's anonymous. In the second case, it's the same data element, but now rec2 is the same elements, but it's going to be of type class 1. So had it been like a record type, a register type, or an instruction type, then the backend processor can collect all the information about registers or all the information about instructions. And so these backend processors know exactly what they're going to see. It's not like you can't add things to the register field for the backend processor. They won't know what to do with it. So, and then some kind of simple things we're already used to, which is like, for example, you can have default parameters. And the thing also to realize is that it is like a template processor in the sense that it doesn't really matter. The parameters that were of the class is basically more like a template, are not really available later on. So if you want to actually have them be part of the data record, you have to actually somehow copy them in. So you'll notice that I'm actually copying hello and P parameter 1 and parameter 2 into a specific component of the record, if that record value needs to be available to the backend processor. So here's actually what the output looks like. If you run the tool, I put it on 2 pages so you can read it better. But one thing that's a little bit irritating, and this is actually kind of a bug so these are like things when you start doing it, you realize nobody looks at this because there's these bugs I found that have been there forever, but actually name should have been class 1. And it's actually used in some more complicated situations, but because nobody uses it in the simple one, no one really ever noticed that it was putting this question mark in. It's just a bug in it. So that's what that's about. So these are basically how it expands. This is the output of the tool, and so it lists the classes first, and then it lists the actual data records. I would have liked to put this on 1 page so you can kind of refer back, but you won't be able to read it then. So here's our record 1. If you notice, it was just the plain 2 fields. Record 2, they put in the comment that it came from class 1, but the backend tool also can find that out, and that's really important. And these are all things that kind of like hung me up because I don't know, I don't really like learning a language by just looking at some example. I like to make sure I understand what it is, and I'm trying to fit a model to what's going on, and I didn't really catch on at first because this is kind of unusual. It's not really a template processor, it's not really a language, it's just sort of something else. And and then here's the one where the actual had the default parameter. Okay, so another thing that's a little confusing that takes a little while is they have this notion, so if you don't actually add you have kind of you can't really tell the difference between an empty class or a forward declaration. And that's confusing when you start to look at some of the more complicated definitions of the different targets. So, and see, one thing too, I really want to write a better language manual because once you start doing that, you find all these ambiguities, and it's kind of like the old days when I first programmed, where if you wanted to know what the language rules were, you ran the compiler because there really weren't reference manuals that were any good in those days, So that's kind of bad. That's like going back 30 years to when people didn't take the time to write the manuals. So here in this case, you don't really know. It could just be an empty class, which they use a lot, or it could be. So in this case, we actually declare the full class later, and it doesn't really matter in this case because by the time you create a data record, you've already defined everything. However, you can actually create this kind of situation where you think it is and you use it, and then you actually do declare it, and it'll actually kind of still work. And it's just like these are all sort of anomalies of the implementation. I don't think anyone intended this to be the semantics of how this language works, but just to kind of be aware of this. So in this case, you're sort of using it as an empty class at one point, and then you actually add something to it. And if you declare another record, it'll look different because now it'll have a class with an extra field to it. So anyway, so here I just created kind of an example. I'm not going to really go through all this in detail. I think a lot of this stuff, if you've programmed, is is sort of obvious, and so I've created these examples. You can look through them yourself later. I don't want to labor through all these things that are sort of obvious, but you can basically declare, like in this case, you can declare like empty types, which are used quite a bit for various things. And here you can create like bit. You can have integer types. You can have sort of the usual ways to make it nicer to enter the data values. A little confusing is the fact that bit in bits is different. So if you want to have, well, it's like Boolean, I guess, in a bit string. And we'll look at it later. I have a more complete example later, but because encoding bit patterns is so important in instruction stuff, there's a lot of features for doing that. And I'll have a whole slide later on of how all the ways you can do that. Here's just a simple thing where you can have either a binary number or you can actually have a list of bits. You can have a list of things, and these all kind of work just like how you would expect. And I have more examples on the website, the Google code, but you can also look at, they have more complete unit tests for lists, so you can look at all these things if you have any questions about that. Hopefully we can, they have this thing they call DAG, which it makes me crazy because it's just a tree. And for a while it really hung me up because they kept calling it a DAG, and I couldn't really see how you would create a DAG with this thing. And the actual data structure in the compiler is a DAG, and you can actually do more complex matching, but in terms of this, it's not a DAG, it's just a tree. And so that was really messing with my head until I realized that they were using it that way. And the only real restriction is that the first root of the tree has to be like a class type. It can't be like a simple type, like a node. So another thing that they have, which is also a little confusing, and I know this seems confusing because I have friends that have done like whole ports by themselves and can't answer really simple questions about Tablegen. They just sort of had done so many compiler ports in their life that they were able to just guess, because they already did a Spark port and a PowerPC port and an ARM port, and they've done these many ports, so they just by looking at the examples they could kind of guess what they needed to do, but actually they just had to cut and paste. So one thing that they have too is they have because there is a way to kind of override like this parts of Tablegen that it's not really powerful enough for what the compiler really needs. So sometimes you have to pass code through to it. So they have this way to basically put code inside of, and basically, I don't know if people know Python, there's essentially like Python, the triple quoted string. You can basically just create, it's a little confusing because actually this left square bracket curly brace is actually a token. So that confused me at first, because I'm looking for like, okay, it's because square bracket and curly brace are already tokens on their own. So I was trying to understand, like, wait a second, this is until I realized it was actually just a single token. So that's what that means. It's like it's triple quote in Python, essentially. And then they have this code as like a data type, but it really just means string. And it'll just translate into string. It's like a documentation thing, so you know that the person's going to use it for code. But those two lines I have, which have different types, will turn out to be the same thing. Okay, now another thing they have, which is a little crazy too, it took me a little while to understand all the semantics, but so they have a way to override a definition that occurred by default. So in this case, class 1 by default is going to assign I to 1, and then when I want to use that for rec1, I want a different value of that, so I can just override that by saying let. So it's kind of like just a regular assignment statement, but the part of it is that the parser is really primitive, so they use a lot of keyword, left context keywords to make it easier. It's just like they use all these kind of recursive descent parsers a lot, and so just to make it easier, they sometimes will stick a keyword in rather than just say like I equals 2, which would have been maybe a little bit more normal. It's just easier to parse by having the word let. I think that's why they did. I don't really know any other reason. So now I'll share a little more complicated example. So here's one where I had 3 components, which unfortunately it's not on the same slide, but it just didn't really fit. So now I can override different pieces of this. I can actually override by kind of encasing it in a loop. So in this case, I just have one thing, but in the next one, I actually can override like both rec3 and rec4. Each component of theirs that has I, I'll make it 3. And j equals 6 and k equals 9. So it factors across the whole set of definitions inside there. And like I said, these are all basically, I think they did them one at a time as they tried to define different machines. They realized, hey, we can't do this succinctly. And they were repeating this field everywhere. They tried to add some things to it. And like I said, I'm hoping to kind of go through this, and maybe other people are interested in working with me on this too at this other site, and we can define this better, maybe really make the language a little more clear and actually make it better by trying to formalize it a little bit. So this one somehow didn't get indented properly, but anyway, this is like a nested one where you can actually have these nested ones, and they use this sometimes. So here, it's just they just factor inside. Like I said, you can compile these examples and look at them carefully, but I think it's self-evident. Okay, and then here's one which probably right now, if you ask me all these questions, I'm going to get the wrong answer. But I did work through these at one point, and I understood this completely. But anyway, they have all these different ways to do bits, and you can have like a binary, just a binary number, or you can have a list of bits. You can assign like ranges of things. So Z is a 3-bit element, and you can take another thing, which is Y, and just take bits 0 through 2. So that's 3 bits. And you can also use it on the left-hand side, which is kind of nice. And a lot of people didn't understand this and realized they could have simplified a lot of their definitions by factoring this way. That's why it's nice too. You sort of get, if you understand what the language really lets you do. So you can just kind of study through this yourself, and you can compile this and see what it actually, what it produces. But and there's a couple of funny things about it. I think I don't know if it's on this slide. There's a couple of cases where you take a bit of something and you think you can use it as a bit, but it's really an integer already. And I think I have an example of that. There's these are just all like semantic anomalies, basically, because the language is sort of just evolving by people adding things to this tool without really writing a manual and having a grammar and defining all these things. And that's the naughty thing that happens when you do it that way. But basically, it works. It produces a lot of compilers, so it doesn't like this. It doesn't work at all, but it could be better. So they have this kind of multiple inheritance, but it's really simple. It basically everything just gets jammed into the top level. So here I have like 2 classes, and then if you look at this, you'll see that it's just going to jam everything inside. Even if you have different levels of it, it's just going to jam it all into one level at the end. It's not going to create any kind of like a real C++ multiple inheritance, but it's okay. So, and here's another thing which kind of hung me up a little bit until I kind of understood what the plan was here. So actually, as many years as I've done this, I don't really usually, so usually when I'm going to use a forward declaration in C++, even if it's for a data structure that references itself, I always declare like the empty struct first. But actually, you don't really need to do that. I didn't really know this. It's really embarrassing. I worked on compilers so much. I probably knew this at some point, but I forgot about this. And so actually, the second form is legal too, where you just have struct C2. It already knows you don't have to forward declare the empty declaration if it's the exact same thing. So they kind of use that same paradigm in here, and I'll show you. They use it for. There's a very complicated example of this. They use the head of every register definition, so it's really important to be straight about this because you'll be confused about how it works. So you can actually create this class where it's like a list of itself, and actually you don't even need the C1. See, in the second case, I don't even use that. I just use C2 by itself. And so it's going to behave kind of like C does there. It's going to, as soon as it sees C2, it's going to like implicitly declare as if it was empty, or not knowing. Like I said, whenever you see that, you never know whether it's empty or whether it's going to be declared later. You don't really know that. So you can create a list of something, and then if the final thing that you declare can have no parameters, then it has defaults for everything, then this will still work. Okay. So this is another thing that's a little confusing. This is another very idiosyncratic thing, and it's so strange for me as from a language point of view that it took me a while to kind of catch on to what they were really saying it does. But once again, they're trying to avoid they're trying to do a simple way to do a lot of kind of common factoring, which they see when you're trying to especially match up the language. So here what they're trying to do is they have this thing called a multi-class, and then if you notice here when it says a def, it's a def M. And so this is, once again, it's a lot of idiosyncratic things. I think it's just because it was easier to extend the tool. Sometimes there's things where normally you would use it, just call it a def because you could figure out from the context, but they just found it easier. And so what it's going to end up doing is it's going to take this name add, and it's going to append it to all the inner declarations. So you'll see in the next slide I actually have what the output looks like. So it's going to add, for everything inside there, it's going to append the name of the thing to all those defs inside of the curly braces. So now this is add M, add RR, and I don't know if you follow it. Some of you will get right away, but if you look at it carefully on your own when it's quiet time, you'll see what it's doing there. It's as simple as this example as I can give. And this is the same ones for. So basically, with like two definitions, you're able to avoid a lot of duplicated work. But it's kind of strange to me that this thing just kind of gloms in, and then all of a sudden becomes this kind of textual insertion at the beginning. I mean, it's sort of language-wise, it sort of messes with my head a little bit to see that, but that's how it works. So then they have another way to do it where you can actually have the def M's inside of the class, and that just creates like another level of all of this. And the easiest way to do it is to really just sit down. Like I said, all these examples they should be part of the talk. It should be there. And I sent him the tar file, but there's definitely at the Google code site, all the examples are there. So you can take a look at that. So just compile them and take a look at the output file, and you'll see what's going on. But I tried to make these, like in the manuals, the examples are more complicated. They have more information, which just confuses, to me at least, what's really going on. So I tried to make this as minimal as possible. So this is sort of the example of this one. So here you get like double levels of it adding things, and so I'll just kind of, unless there's any question, I think you'll read through it. You'll see you get the idea. I think already. You can take a look. So so I'm not going to try to like go through all the back-end processes. There's quite a few of them. There's like about 20 of them, I think, and basically they're all looking for certain syntax of record definitions. And so like I said before, once you understand that, you realize you can't add anything to them because they won't know what you're doing. And what I realized is that there was a mistake in every register definition except for Intel, where somebody had started to do something and they had added this field to it, and then everyone after that just kept copying it. All the ports have it. And so you realize that it doesn't hurt anything because it's just going to be ignored. But that's an example where this thing just has already been duplicated in many places. And when I brought it up, someone said, yeah, there was like some history of they were going to do something but never really did it. But everyone's afraid to touch it. And actually, one of our guys, who was one of our main MIPS guys, he actually asked the original guy that did the MIPS port, can we take this out? And like everyone's afraid to touch this thing because no one really knows what it's there for. But once you understand how this thing works, you realize you can throw it away. And when I asked, someone said, yeah, you can just throw that away, or whatever. But so one thing that they do, which is one of the more complicated things in the whole thing, which actually is the very beginning of every register file, that's why I spent a little time explaining this, is they have a lot of things in the definitions to figure out when registers have like sub-registers, especially like on Intel, when you have like all these, like AH is part of AL, and so you have to be careful. The code generator has to know that when you touch AH, you've also touched AL. And so it has to have a way to give like to understand when registers have like sub-registers or dependent registers that are dependent on it. And so they use this funny concept to me, which is a little strange, called sub-register indexes. And I'll try to give an example of this. This is actually one of the craziest, the hardest things to understand, but it's essential in the very beginning of all of them. But once you do this, I think if you go through the architectures, hopefully you'll be able to do this and understand it yourself. We just talked about this. So So what they essentially do is they create like parallel arrays. So this data language is somewhat limited. So they'll create these parallel arrays and you have to line them up, and that's really what the subregister indexes are. So they'll have, like, for AH and AL, you could actually write it either way in the register definition and it would work in both ways. And it's mostly, I think, basically just limitations of the power of the data definition language. So they have to define this kind of name that they can use as a parallel index later on to search for in the tool. And so that's what these subregister indexes are. And I think I have given an example. I tried to give a simple, make a little file of this. Let's see. So there's one for MIPS too, an example where we have the double precision floating point register can be thought of as two single precision floating point registers. So I tried to basically make up as simple as possible version of this. And so remember I talked earlier about this thing where you can just create a type right away. So this class subregister index, once it sees that name, it's almost as if you had a forward declaration of it. So now you can use that name. It's considered like an empty declaration now for all intents and purposes. So basically you can have a list of these subregister indexes. These are like components of the register, essentially what it will be used for. And then when you declare the register, you can have its subregister indexes. And so let me just, I think on the next page, I think it goes over to, so some of them don't have subregister indexes, but here's one where it really does. And basically you have these kind of parallel things that line up with each other. So you'll have the subregister indexes, and that tells you what it is, and then you'll have actually the names of them, and it's like in a different list. So that's how they line up the two. They have like these basically parallel lists, and so the back-end tool is going to, if it looks for, like, so there's a whole class of things that are these 8-bit subregisters, high and low in Intel. And so when you declare any of those class of registers like AX or BX or whatever, you can leverage off of that and just list the two pairs, and this part it'll pick up from the fact that you did this let. This could really, you have to kind of sit down, and some of you are really probably quick and you probably already figured this out, but you just have to, if I labored here, I think I'm just going to be confusing everyone, but this is a good example. I really tried to boil this down. I think if you go through this and understand it, you'll save yourself some time. So that's pretty much my talk about this. I don't claim to be an expert on this either. I didn't write this tool, but we do use it, and I do try to read through the architectures that I knew, and I can pretty well understand them now after having kind of gone through this exercise of trying to deep dive into some of this. And I hope in the future to really document all these back-end tools, because they're basically all assuming a certain set of record definitions, but it's not documented anywhere. It's all just sort of done by example, and a lot of it, if you just look at it, you can kind of grok what to do, but it'd be better to have something more clear. So, yeah. Questions? Or?
Can we go back one slide?
Uh-huh. If I know how to do that, let's see. Okay.
I have no question. I just want to look at it a bit more.
Oh yeah, sure, no problem. Yeah, this is unfortunately is at the head of every single register definition, the most complicated part of it. This is.
Yeah. So, I mean, do you think it's mostly just a matter of documenting this thing, or maybe the whole language should be sort of reformulated?
I would redo it. I mean, there isn't really that much code of this written already where you couldn't redo it. But I think it's, before I would probably document it first so we understand what it's really about, and then start thinking about, because right away you start to have issues if you start to document. You see, well, this, and like I said, I think I would like to see a more, in the past there have been nice languages for specifying, for doing this where you can more, like with, there's a primitive data type of a DAG, so now you can really, do these things very succinctly, almost like a paper. So I think it could do a lot better, but I think that you probably would have to start by documenting it and trying to generate a dialogue about what to, it's a community thing, so you can't really just start stepping on people and saying, I don't want to do this thing because it's not going to fly. So I think first step would be to document and then start to, talk about things where, okay, this is really unclear, what's the rule here? And so I don't know. I would probably think we'd probably end up something different later, but there may be some ideas that work out nicely. I don't know.
What's it like for error checking? I mean, does it catch mistakes pretty
It does catch some things, like if you try to, things that are the common things that would have been problems, it catches very well. Like if you try to assign a bit field that's too big for one, it'll catch that. Because that's a common mistake, and you're trying to type something and you don't give enough bits for it, so it'll look for those kind of things. It does crash quite a bit, if you give it bad things, and that's irritating. And there's a lot of these tools too, so you can, I haven't really deep gone into it, but in ours, we obviously use all this for the MIPS compiler, and one of our guys was starting to work on the assembler, and it was crashing on some of the input, and because it's a different back-end processor part of that, and you just have to go debug the program at that point is what happens. You have to sort of, if it's complicated, now you have to basically bring up Tablegen and GDB and try to understand, what's going on in there. And not everyone knows all these parts of the tools. People, some people know a lot about different things, but maybe don't really know much about front-end tools, so it can be difficult for them to understand parts of what's going on there. So that's not really necessarily a good situation.
There are a lot of features that look like they should be generic, but only work with a particular use case they're actually coded for or used in the files.
Yeah. Yeah, so I think there's a good, we need to really go through and scrub it and try to, but like I said, there's not really more than a couple thousand lines of TD, it's not tons of this code, so if we had to use a different one, I don't think it would be a huge problem, but the usual way in LLVM is just kind of incremental changes, so I think we have to start with. My guess, even if you define a language, I think a lot of the syntax would just get grandfathered in because you would have a lot of resistance to really, redo it totally unless you had a good, good reason. But hopefully this area we can, this little Google code thing, if people are interested, we can talk about it and then maybe get some of it back in the mainstream. So yeah, and I would suggest going through, you can go through and try to read these now. There is a generic set of table definitions, and those are basically the interface to the back-end processors. And they define registers, and then for specific ones, they create their own version of them. So if you read through those, I think you'll hopefully after this talk, it'll make some sense, especially if you read the other documents.
So now we can email you with all our questions.
You can if I can. I'll answer them if I can. There's some people that know more about this. I'll certainly be best to post it on the dev list, and whoever knows will answer.
So, I mean, I don't know how much you've looked at this, but I mean, is it relatively easy to add new backends to this? I mean, because there are lots of places where we have tables, right?
Right.
So, I mean, I suppose the question is, sort of, what's the, what do you think the sort of man-hour spin-up time is for a relatively simple backend?
I don't think it's that hard. I mean, if you look at it, it seems like they have some kind of it's like some sort of an abstract, just a really simple abstract data structure of all the parts that you can register things for. It's sort of a simple. It's not too bad that way, but then your backend has to be added into the one that if you write a backend that does something that's totally unrelated to code generation, it's still going to be part of this tool. You have to link it in.
Yeah, they all get linked together.
They all get linked together, yeah.
They split like at least Clang and LLVM.
Oh, right, that's the thing. The Clang has its own table, doesn't it?
Yeah, so they created a leaf Tablegen and they split Clang from LLVM ones.
Yeah. So, yeah, I mean, probably it'd be easier to do it too with some kind of, a DLL where everyone creates their own shared object and then it uses some kind of configuration file rather than linking all these in. And you can, because also too, if you wanted to just have your own that was just for yourself, and you didn't want to check it into the tree, it's now you've got a real problem. So, hopefully create some dialogue and some ideas. Like I said, I don't really know.
Oh, I was going to ask. So in the backends, the pattern match.
Right.
Can you go over like what, because the order matters somehow, right? And then there are the patterns, and then there are the patterns that are included in the instruction definitions.
Yeah.
Do you know how those?
I know it to some extent. That would be like a different talk where I could really go into I'd have to go into that specific back end, because they're all different. Like you have to go in through how it uses the DAGs and what rules it uses and that kind of thing. Basically, people just do it by like example. And that's that's kind of dangerous, because then you can miss the, you can think, oh yeah, I see this pattern, of the examples of how this works, and then you go to use something, and you can get subtly, compilers is a dangerous place, because you can get subtly surprised by things. And like in my group, I don't let guys put any optimizations in if they can't explain to me how they're going to test it. Like that's one of the bars. If they're just saying, well, probably there's a lot of code in there, that usually won't get the, or it's going to be an optional feature until they can show me how they would test that. So for some of the other stuff too, if it's not defined well, it's not clear that everyone really has the same understanding of what that thing is. And
So the type coercion that happens in the matching, is that something that's specific to that backend also, or is that?
yeah, so think about the backend as basically you've basically created an XML file.
Yeah.
And what does XML file mean? It means nothing. It means all those strings only mean something to whatever tool reads it. And that's basically what it is. You can have a set of tool backends that have some common data definitions, so they all understand like what the registers mean. And so a lot of the backends ignore a lot of the records, but they could also assign different meanings to them. I mean, it's just like I said, you can just think of it as a macro processor for XML as the front end, and then there's a back end, which they're just strings. It means what it means to the back end processor. But none of the back end processors are documented at all. Loosely in some of the other manuals I mentioned, but nothing is like, there's comments in the code you can go and see. If you work on compilers, it's like, okay, I kind of get the idea of here, but as it gets more involved, it's really a little scary if you don't know it all.
Probably got time for one more question. Okay, well then, thank you, Reed.
Okay, thanks.